All right.
The requirements for 331 is just in Calc 3.
Yep.
That doesn't make any sense.
No, it's, well, ostensibly it's to attract engineers, but I don't know. In any event, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, and just ask that you'd help us to use this time wisely, that you'd be glorified in what we do, and we just thank you for your many blessings, Lord Jesus. In your name I pray, Lord Jesus. Amen. So, the good news is, I believe Dr. Skimbortis will be back for you guys Monday. So, I must extract my pound of flesh from you today. And so I decided to skip ahead to chapter 8 and talk about the theory of linear transformations, all right? Because I suspect what Dr. Skimbortis is likely to do is to start either reviewing for your test or maybe going into eigenvectors. And I don't want to talk to you guys about eigenvectors unless I've got at least like 3 class meetings, all right? So, and I really, truth be told, you really should talk about linear transformations before you talk about eigenvectors in this course anyway. So the book is wrong. And here we go. So what is a linear transformation? So given vector spaces V and W over field F, we say a function, which is usually called a map in this context, T from V to W is linear transformation if T of Cx is equal to Ct of x and T of x plus y is equal to T of x plus T of y for all x comma y in V and C in the field. All right. Various notations exist for the set of all such things. Like some people would say that like T is an element of the linear transformations from V to W. Right? T is an element. T is a linear transformation from V to W. Another language you might talk about is that if T is an element of linear transformations from V to V, then you can just say that T is an element of linear transformations on V. And sometimes that's also denoted like end V. This is, the set of what are called endomorphisms on V, linear transformation from a vector space to itself. All right, so anyway, there's a variety of notations people, yeah?
What's the fancy L?
Just L, just a fancy L.
What was it supposed to be?
That's the set of all linear transformations from V to W. So T is an element of that, yeah. Now, so great. The next thing you want to know about is, what's the structure of LVW? Is it a vector space? Like, what can we say about it, right? Now, typically in my examples, I take the field to be R because I like to keep it real. But that field could be complexes. It could be integers mod P. It could be, there's so many things. There's lots of fields out there, lots of ones that you don't know about yet, all right? Probably Math 422 is really where we scratch that itch most forcefully. But anyway, so definition, if we have T and S in linear transformations from V to W, then T plus S and CT are defined by the pointwise rules. What are those? So like T plus S of x is T of x plus S of x, and also C times T of x is C times Tx, all right? And that's for any C in the field and X in the vector space. So you can add linear transformations and you can scalar multiply them. Theorem. Linear transformations from V to W is a vector space over the field F. With respect to what would the operations of this vector space be, do you think? Just what I've wrote above, right? Like it's addition of functions and pointwise scalar multiplication. That makes this into a vector space. It's a little bit more than that, though. See, because, well, actually, okay, that's it for now, but for that. But here's the additional definition. If we have, let's say, T and S endomorphisms, then, oh, I guess I shouldn't define it that way. My bad. So sorry. Let me not waste you. Let me try this. Let's make more of this definition. So, all right, here we go. Oh, man. So now I need 3 vector spaces. So we've got T, which goes, let's say, from V to W. And let's say S goes from W to, oh, I need another letter here. How about U? Right? Here, U, V, and W, all vector spaces over F. And I want to assume that S and T are both linear transformations. Okay? Then, you know, if T is an element, I guess I should have just said this to start with. T is an element of linear transformations from V to W, and S is a linear transformation from W to U. We define, let's see here, S composed with T, I think that makes sense. S composed with T, which would be a mapping from what? From V to U as follows. And in fact, this definition really has nothing to do with linearity, does it? Like we could just as well make this definition set theoretically for any pair of maps. Even if they weren't linear, this definition would still be like legit. And it's the definition you saw in pre-calculus, just the composition of functions. Does that make sense? T of X is an element of W, the domain of S is a W, so yeah, it's a good formula. And it's single valued because T of X is a single value and S is single valued. In other words, the composition of functions is a function, right? Great. So that's how we define the composite of 2 linear maps. Here's a cool thing. Theorem. S composed with T is an element, is itself a linear transformation from V to U. In the context of what I've just given you, the notation that I've set down. In other words, the composition of linear transformations is once more linear. Let's prove that, yeah? Here we go. Or to quote the Jeff, let's go. Let's see here. S composed with T, and we'll do our we'll do it all at once. Cx plus y, all right? 2-step linearity test. So that is going to give us an S of T of Cx plus y, right? By definition of composite. Next step, we use the linearity of T. Linearity of T gives me C Tx plus T of y. All right? And then what? Well, then by linearity of S, I've got C S of T of X, right? Plus S of T of Y. But then, what are we looking at here? I think I never moved the camera. Yeah. It's okay, everyone's here, right? So then what? Then what we have is C times S composed with T of X plus S composed with T of Y. Hooray, we're done. That proves that S composed with T is linear, right? Because you can put Y equals to 0 and you get the homogeneity, the fact you can pull a constant out. And you can put C equal to 1 and you get the additivity. That the composite of X plus Y is the composite of X plus the composite of Y, right? So we have both pull scalars out and the additive property. Therefore, the composite of linear transformations is once more a linear transformation. So far, so good? You'd like this for a test question, right? Like I would, personally. What else can we say? Definition. All right, so here's it goes. If we have T is a linear transformation from V to W, is linear, and there exists T inverse from W to V, also linear, then T is an isomorphism. Right, an isomorphism. So an isomorphism is a bijective linear transformation. An isomorphism is a bijective linear transformation. So in other words, it's a bijective, which means what? One-to-one and also onto, right? Or if you like to be French, you could say injective and surjective. Right? You can thank the Bourbaki for that mess. You sound smarter when you say injective or surjective, right? But it's just one-to-one and onto in the commoner's language. Anyway, so that's an isomorphism. Have you guys talked about isomorphisms in here yet? No? Okay. So, but you have actually. Let me see some examples. Consider the following. If I say V is equal to, say, second order polynomials over R, all right? In other words, the real span of 1t squared, right? And I can let W equals to R3. Okay? So, if we look at T of, let's say, A plus BT plus CT squared, can you guys tell me a formula which would make this linear? Ooh, but I need something in R3. So let me, I need a column vector, you know? There's no T's over here, though. We're in R3, so we just need...
ABC.
Yeah, ABC. There you go. What's the inverse to this map? By the way, you guys use this notation? I hope you do. I use this notation, so just so you know, that is my sneaky notation for column vector, written as a row vector. All right. If I do square brackets, it's an honest row vector, but with the parentheses, it's a column vector in disguise. So anyway, inverse ABC is, well, A plus BT plus CT squared, right? Have you guys talked about this linear transformation already? Maybe, maybe not. I don't know. It kind of depends what you guys did when I wasn't here, you know? But here's my usual notation for it. And I don't think this is the notation in your book, but it's a good notation. If we have the basis beta equals to 1t and t squared, right? That's a basis for this three-dimensional vector space of possibly degenerate quadratics in T. And with respect to that basis, the coordinate vector with respect to this basis of A plus BT plus CT squared, well, the coordinate vector of that is ABC. So in fact, the coordinate map, which you've already learned about, right? Because you talked about coordinates of vectors in an abstract vector space. The coordinate map is a linear transformation. And in fact, it's a bijective linear transformation. The coordinate map is the fundamental example of an isomorphism. In fact, the coordinate map shows you that any vector space of dimension n is isomorphic to Rn, if we're keeping it real, or Fn, if we're not keeping it real. Okay. Now, I have other notation for this. For me, I would also call this like phi sub beta of A plus BT plus CT squared. That's my notation for coordinate map. All right? You're like, okay, well, that's great. Why do you care about this notation? Well, let me show you. So if we have a linear transformation, let me talk about the matrix. For T, a linear transformation from V to W. And so,
What did you say that symbol was called again?
oh, that? Sideways TIE fighter? Or is it a TIE bomber? No, it's only got one fighter, right? It's capital Phi. But you can call it whatever you like, really. So let me draw you guys a picture. This is how I think about linear transformations. Like, there's a lot of different things we could do today, and I'll try to do a lot of them. But the next thing that's come to mind I think would be helpful for me to share with you is the matrix for a linear transformation. So here's the picture I like to draw. Up here, you've got V. Over here, we've got W. You have the linear transformation T going from V to W. All right? And if we have a basis, let's say beta, V1, Vn, n as in nanu nanu. And over here we've got basis gamma, W1, Wm as in like coordinate map phi beta. That gets me down here to a copy of Rn as in nanu nanu. And I can take a coordinate map over here, phi gamma. That gets me down to a copy of Rm as in mama. Now, notation, guys. L sub A is a mapping from, let's say, Fn to Fm. for A, an element of F m by n, so an m by n matrix. And the definition for L sub A is simply this: L sub A of x is equal to AX. That defines a linear transformation, right? In fact, there's a theorem that any linear transformation from Fn to Fm can be obtained in this way. It's the case that a function from n column vectors to m column vectors is a linear transformation if and only if the formula for the function can be written as matrix multiplication. This is true. You can prove this. Okay? I could take 5 minutes and prove it for you. But that is just a notation. So like left multiplication by a matrix, all right? So what I'd like to discover is, oh, and I guess I'm keeping it real now. Do you guys want me to keep it real or keep it unreal? Student's choice. Real? All right, fine. So down here, I would like left multiplication by some matrix. And that matrix we're going to call this beta comma gamma. So what this means, this notation, is I'm looking for the matrix which is based on using the basis beta for V and the basis gamma for W. All right? And so how would you understand that? Well, you can use this diagram to set up the formula, you see. So if I pick a vector, let's say V up here, then that gives us the coordinate vector V beta down here, right? And that maps over here to T of V. TV is an element of W, all right? And under the coordinate map, that gives me a vector down here, TV of gamma. Okay? So specifically then, the matrix which goes from here to here in the following sense, like we want this to happen. We want the matrix beta gamma, when it multiplies V beta, we want it to be equal to T of V acting on gamma. So that actually defines, that's one way of defining the matrix of the linear transformation. But let me show you how we can understand that definition in a slightly more diagrammatic fashion. So check this out, guys. If I want to, I can follow the diagram like this. All right? So what do I mean? So we're looking at, I want to write L sub T beta gamma is equal to what? All right, so the last shall be first in composition, right? So the last thing is phi gamma. The next to last is T. And then to go the other way, the inverse. So phi beta inverse, like that. And that's straight up a formula for the left multiplication of the matrix we're trying to define. So like, you guys know the, by the way, what is this in terms of your like 221 notation? This is the standard matrix of L sub A, right? Like this is the matrix that gives you the linear transformations action. We call that the standard matrix in 221. How do you find, the, you know, like a column of the standard matrix? What would you do? Like what would column, let's say column I of, you know, the standard matrix of this be? It should be nothing more than L of T beta gamma acting on what? Acting on EI, right? You feed the standard basis into the linear transformation. That tells you the column, the corresponding column of its matrix, right? So let's sort through what that looks like here. So what we're looking at is phi gamma composed with T composed with what? Phi beta inverse. Now I need to talk about some things here. So the coordinate map, phi beta of vi is equal to ei. Conversely, the inverse coordinate map goes the other way. So like the coordinate map trades the abstract basis for the standard basis. The inverse to the coordinate map goes the other way. It takes, to each standard basis element down here, it assigns the abstract basis element up here. So when I look at phi beta inverse of ei, I get nothing more than vi. See, this acting on that gives me vi. Then what I'm looking at is phi gamma of t of vi. Or in my other notation, t of vi in terms of the gamma coordinate basis. But that's exactly what that means. See, this suggests that if we want a specific formula for t beta gamma in terms of the bases involved, what you do is you find the coordinate vector with respect to the gamma basis of the first coordinate in the basis for v, and then you find the coordinate vector of the image of the second thing in the basis with respect to the basis for w. Sorry, I'm messing up my v's and w's, but the formula I'm writing is true. So I'll get out of the way here in a second. So there you go. There's a stone-cold formula for finding the standard matrix of a linear transformation from like a vector space V to a vector space W with respect to a pair of bases. See, if we're working with an abstract vector space, how many bases do you have to choose from?
Infinite amount.
Infinite amount, that's right. So this is not uniquely given. Like if you choose different coordinate maps, then this matrix would be related to that other matrix by a particular transformation of coordinates, similar to like what Dr. Skambordis was talking to you guys about before I got here. Okay? Your question? Yeah?
Yeah, I'm a little lost at like the practical, like I'm confused with the coordinate mapping. Is like, can you like give an example of what a coordinate mapping?
Mm-hmm. Sure. Let's see here. So let's see here. All right, let me think of something. So example 2, we might look at, let us say, t of f of t equal to, oh goodness, let's go with like f of 0, f prime of 0, and f of 1. All right, and this is for f of t, an element of the span of, let us say, 1t, I'll keep it relatively simple, 1t t squared, all right? So you can check that this defines a linear transformation of linear transformation from polynomials, quadratic polynomials, to R3. If you'd like, I could do it to like something more abstract. Is that good? You want more abstract or less abstract?
It's fine.
It's fine. Okay. So if we look at this, then the formula here, if we have t of like a plus bt plus ct squared, then that's equal to what? If we plug in 0, we just get the a. If we plug in f prime of t is what? B, that's just it. That's just b, right? F prime of 0 just gives me b. And then what's f of 1? Yeah, a plus b plus c, right? Ah, man, I regret this example. It's going to be hard for you guys to appreciate rats. Let me dial it back a second here. I need to make it weirder. Otherwise, you're not going to appreciate what's going on. So let me put it in a matrix, A, B, and 0, and then we'll put A plus B plus C there. There, no, that's weirder. You happy? So here, and of course we could write that as, you know, f of 0, f prime of 0, and down here is f of 1, right? Did you move the camera, Jeff?
I did.
Thank you. All right. So you can check that this is in fact a linear transformation. Now where's the linear transformation to and from? So here we're looking at a linear transformation from, you know, P2 of R to what? To R 2 by 2, all right? So to find the matrix of this transformation, I would need to give a basis for each of these spaces, right? So let's stick with this sort of easy choice of basis for P2. This will let be beta, all right? For gamma, we'll use the usual matrix units, right? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That is a basis for our 2 by 2, okay? Our 2 by 2 is a 4-dimensional space, is it not? Right? Okay, so then let's work it out here. So we on the one hand, if I think about my v being f of t, right? Let's think about this. So what's the coordinate of v with respect to beta? And I'm sticking with this, this arbitrary one, a plus bt plus ct squared. To to find the matrix, you have to sort through an arbitrary input. Okay. Okay. So like this has coordinate vector ABC with respect to the basis beta, because the 1 came first, the t came second, the t squared came third. All right. Watch out for that. If the basis was t squared t then 1, it would be CBA instead. Yeah.
I have a clarifying question. So the beta is the basis for the P2.
Basis for P2, right.
Gamma is the basis for the R2.
That's right. I'm thinking of this as V and this is W in my general discussion. I'm trying to give you an example. So, great. Well, this right here is T of V, right? So T of V is right here. Yeah. So what's the coordinate of T of V in this context with respect to gamma? We're asking what's the coordinate of the matrix A, B, 0, A plus B plus C. All right, great. Well, that is A, B, 0, A plus B plus C. All right? So we now have calculated the coordinate vector of an arbitrary input, the coordinate vector of an arbitrary output. Now we're in the position of asking what is the matrix of the transformation with respect to beta and gamma. So if I do that, here's how it goes. So what we're trying to do is figure out what this matrix is. We don't know what it is yet, right? But if we multiply A, B, C as our input, our output is supposed to be what? It's supposed to be A, B, 0, A plus B plus C, all right? So what kind of matrix should we have? We're going from a what? From a 3-dimensional space to a 4-dimensional space. We expect a 4 by 3 matrix. So this should be a 4 by 3. And we call this matrix T beta gamma. That's its notation. At least that's my notation. Anton might have a different notation that's stupider. That's a good notation. It tells you everything's going on. So what do I put my first 4-component row for? What should it be? 1, 0, 0, 0. Okay, I'll take it. How about my next row? Wait a minute, 4 by 3. Maybe, yeah. Sorry, guys. There we go. 0, 1, 0, 0. How about just 0, 1, 0? 4 by 3. Okay, yeah. Let's remember the basic thing. Oh, and then this is 0, 0, 0, and then I heard a 1, 1, 1. Yes. There you go. That is the matrix of T with respect to the bases beta and gamma. Now, you can easily derive the formula. You can easily derive the formula if you had selected a different pair of bases. All right? If you selected a different pair of bases, like let's think about this. On the one hand, we have that L of T beta gamma is equal to, what was my formula for? We worked it out over here. Phi gamma composed with T. Phi beta inverse, right? You can solve that for T. T equals what? If I solve this for T, what I have to do is compose with phi gamma on the left and compose with phi beta on the right. Then they'll. So what we got then is phi gamma inverse composed with left multiplication by this matrix multiplication here composed with phi beta. All right? Now T is defined independent, actually, of any particular basis. I mean, like T is a linear transformation of the vector space. It doesn't really, you could choose the basis to be something else. It wouldn't change what T is, all right? So think about this. If I chose chose a basis instead of beta and gamma, suppose I chose beta bar and gamma bar, what formula would I write then? Like I could do the same thing for a different choice of basis, right? I could do that. If I did that, that would give me the same thing but with bars instead of not bars. So like this would be equal to phi gamma bar inverse composed of the left multiplication by the matrix with respect to the barred coordinate systems, barred basis composed with phi beta bar. See, because T is equal to T. But then, once you have this, you can easily derive the relation between this and that. See, L of T beta bar gamma bar is equal to phi gamma bar no inverse composed with phi gamma inverse composed with L of T beta gamma composed with phi beta composed with phi beta bar inverse. But what you're looking at now is a composite. So let me just kind of recap what's going on here. This is in fact a linear transformation from Rm to Rm. So this is going from Rm to Rm. This right here is going from Rn to Rm. And this guy right here is going from Rn to Rn. And as such, we can apply the theorem that we have from 221 that the matrix of the composite of linear transformations on Rn, right, is the product of the standard matrices of the transformations being composed. In short, it gives me this rule. The matrix with respect to a different choice of basis is equal to the matrix of this animal. This is the so-called change of basis matrix. And then you've got your T beta gamma. And then you've got your matrix of phi beta composed with phi beta bar inverse. That is the general rule for changing coordinates for a matrix for a linear transformation from one vector space to another. Now you've seen this formula before, but what you did is you looked at the particular context that you're just talking about a linear transformation from like Rn to Rn, maybe R3 to R3, and like you call this one matrix P, and you call the other matrix P inverse. Because when it's the same vector space, those become the same matrix and its inverse. And so then you get the result that the matrix of a transformation from matrix of an endomorphism, if we use the same basis for like the domain and the codomain, the matrix of an endomorphism is similar to the matrix of any other coordinate representation for that linear transformation. Anyway, this formula I think is pretty challenging to derive in other ways. But with this diagrammatic method, I know you guys are probably like lost a little bit, that's fine. You can actually think through this and derive the coordinate transformation rule for yourself. It's like not that hard actually, if you really look at what I just did. Now, to actually flesh out what these matrices look like for a specific example, yeah, that takes some time, sure. Coordinate change is hard. I didn't say it wasn't. Anyway, now, you asked me like, you know, why? Well, the ultimate reason why is because we'd like to understand the structure of like linear transformations, right? So if you can find the matrix of a linear transformation, what that does is it gives you a snapshot of what the linear transformation is independent of the abstract vector spaces, right? It's giving you a matrix that has all the information about the linear transformation. And because these are isomorphisms, it means that things that are true about the linear transformation will also be true about the matrix of the linear transformation. So you can study the properties of the linear transformation by studying properties of the corresponding matrix. For example, two important things about any linear transformation that you can talk about are we can talk about what's called the kernel of T. I think your book uses like lowercase kernel, whatever. And we can talk about the range of T, which I think your book just calls range of T. But kernel of T is x in V such that T of x equals to 0. And the range of T is defined to be T of V. So that would be T of x in W such that, you know, x is an element of V. And so both of these I'm defining for T a linear transformation from V to W. There's something called the kernel, and there's something called the range, all right? And so, like, just to, you know, still kind of answering your question about, like, what's the point? No, that's a good question. I'm not sure I'll really get the point across today. I'm trying. But, so, like, one of the things I had intended to do today, but oh well, time got away from me. You can easily prove that the kernel is a subspace of V. You can easily prove that the range is a subspace of W. All right? These are special subspaces associated with the linear transformation T. So a picture of that, maybe something like this. There's a subspace like this. This is kernel T, all right? So you could look at the image of that subspace under the coordinate map. That would give you a subspace down here. So that would be like phi beta of the kernel of T. It's not hard to prove that the image of the kernel of T is exactly the null space of the matrix of T with respect to the beta gamma basis. But you already know how to find a basis for the null space. You row reduce the matrix, right? So in principle, you can, whatever complicated transformation you have, you can find a matrix of it, do row reduction on it, find a basis for the null space, and then what do? How do you find the basis for the kernel upstairs? You simply take the inverse image of this and go back up, because there's an inverse. You can, like, anything that's in the basis for the null space, you can, like, just take the inverse coordinate map and put it back up here, and that will give you a basis for the kernel. Likewise, over here, there is the range of T. Guess what? The image under this map over here would give you, well, that would give you a subspace of Rm, since we're keeping it real. So phi gamma of range of T, that would be a subspace of m-dimensional column vectors over here. What do you guys think that is with respect to the matrix of the transformation here? What do you think?
Column space?
Column space of what? Yeah.
The T of beta gamma.
That is correct. So, check this out. The dimension of the kernel of T plus the dimension of the range of T, right, is equal to what? The dimension of the null space of the matrix T beta gamma plus the dimension of the column space of the matrix T beta gamma, right? What's that equal to? Well, this was what? The number of non-pivot columns in the row reduction. This is the number of pivot columns in the row reduction. But what is this? This is a what by what matrix in this context? It is a m by n, I believe. M by n matrix. So this is equal to n. What is n? It's the dimension of B. Yes, it's the number of columns in the matrix, but more interestingly, it is the dimension of the vector space that we're starting with. So this is the rank nullity theorem for linear transformations. The dimension of the kernel plus the dimension of the range is equal to the dimension of the vector space you're mapping from. I have just stolen that theorem from the corresponding theorem for matrices using coordinate maps. That's ultimately the use of coordinate maps, is they allow us to a systematic thievery of things we already know about matrices for things we'd like to know about linear transformations. Now, there's another way of proving things about linear transformations, which is through direct, elegant, algebraic argumentation, right? And that's probably a better way to be in here. Now, if I was to go down that path, I would start proving things like the following. First of all, I would prove that the image of a linear combination under a linear transformation is a linear combination of the images of the vectors. Lemma number one. Lemma number two, if the kernel of a linear transformation is 0, then the image of a linearly independent set is again a linearly independent set. You could prove this. All right? And you just start developing theorems like that, and you can prove the rank nullity theorem through direct argument like that, independent of using these coordinate maps. Now, my proof still has a hole in it because I used a specific choice of basis. How many choices of basis are there? Infinitely many, right? So I'm obligated for the full proof to prove to you, first of all, that the equations I wrote down are actually legitimate. I just made you guess. But second of all, that it's independent of my choice of coordinates. All right? But the fact that that's true ultimately rests on other theorems, like you can prove that the composite of isomorphisms is an isomorphism. All right? So these are, if I had more days, I'd do that with you guys, but you're freed of me. I think you're freed of me. This is probably the last time you'll see me. at least in here, unless, well, let's hope that doesn't happen.